how would you go about approximating the length of a curve? What I mean by that is you've got an xy plane like this, and you've got some curve like this one. If you want to know how long this curve is, like if you have a flexible tape measure and you lay the tape measure directly on top of this entire curve, what would that tape measure read from here to here, you know? One thing you could do is you could say, well, I understand how to take the length of a line. So I could make a line from here to here and figure out the length of this line segment. And if you don't know how to do that, well, you could break it down into a horizontal component and a vertical component. And if you know the difference between these x coordinates and you know the difference between these y coordinates, you can find the hypotenuse of this triangle and give you the length of this line segment from one orange point to another. And then you could take another point, like say here, connect it up and find the length of that line segment, and another point here, find the length of that line segment, and then add up these 4 line segments, and that would give you a pretty close approximation of how long the blue curve is from one end to the other. And if I increase the number of line segments I'm using, instead of 4, maybe use 5 or 6 or 7, the approximation should get better and better, right? So I think that's what I've got if we follow this link here. What you see is what it would look like to take the length of this blue curve from one end to another if you have only 3 line segments, 4, 5, and in green I've got the actual length is actually 8.147, and right now this approximation is 4% off, which I feel like that's like really good, you know, for such a crude approximation, 4% is not that bad. But the idea is if I were to continue to increase the number of line segments I use, at 9 line segments, the relative error is only 1%. And if I increase to 20 line segments, the relative error goes down to 0.2%. And obviously, the more line segments I use, the closer fit I have to this curve, and then the better the approximation becomes. In the limit, as n approaches infinity, I've got infinity little line segments across the curve, then it should be perfect. It should be exactly the length of the curve.
How do we do that in Desmos?
This, I don't know, I did this several years ago when I first started teaching. I could share it with you, and then you can go and look at the formulas and stuff, but I mean, it took me a while to do this in Desmos. But yeah, I can try to remember to post this on Moodle maybe later. But to find the length of the curve, we have a formula for finding the length of a curve. And specifically, this formula I'm showing you on screen is one for a parametric curve. So if you've got x defined as a function of a parameter t, and your y-coordinate, same thing, as a function of a parameter t, then this is how you could approximate the length of the curve, where a and b are the lower and upper bounds of t. And the explanation for why this works is you say, well, this is the point where t is equal to a. And so this will be the point where t is equal to b. And at every little place along this curve, we are going to have some kind of line segment. And I can break my line segment down into a vertical component and a horizontal component. And this horizontal component we'll call delta x for a change in my x variable. And the vertical component we'll call a change in y, the vertical direction, so delta y. And then this curve isn't quite it, but it's almost like a hypotenuse of a right triangle. Maybe not exactly if it's got a little bit of curvature, but the hypotenuse is approximately the square root of delta x squared plus delta y squared. And then what we'll do is not just take the length of that line segment, the hypotenuse of that sort of triangle, but also add up all of these hypotenuses. And then what would it look like if I multiply this times delta t divided by delta t? Because I'm allowed to multiply by 1. Multiplying by 1 doesn't change the value of anything, and delta t divided by delta t is 1. Well, then I could distribute the delta t from the denominator into the square root. And when I do this, I can square the delta t because I'm taking the square root. So squaring it and then taking the square root. It's what you have to do to keep it balanced and everything. And so that's an approximation for the length of my curve. And if I want to make this approximation exact, what I should do is then take the limit as the number of these line segments approaches infinity. And as the number of these line segments approaches infinity, the t variable is, of course, bound up between a lower bound and an upper bound. So with a fixed interval and splitting this fixed interval into infinitely many segments, then that means as n approaches infinity, the delta t has to approach 0. So we want to take this particular limit of this sum and since this is so much to write, people of course invented the integral notation to represent the kind of limit you're taking as you increase n to infinity and delta t to 0. In the integral notation, we just say what the lower bound is and what the upper bound is, and then the integrand will be the square root of. As delta t approaches 0, delta x and delta y are also going to approach 0, right? As the length of this segment goes to 0, the horizontal and vertical components are going to 0 as well. And so we're going to call this limit the dx dt, where lowercase d indicates that these are like small changes that are approaching 0. And then delta y delta t is going to become the ratio dy dt. And this is the formula. So the weird square root in the integrand is really just coming from the Pythagorean theorem. That's what I'm trying to illustrate here. The curve length formula is just applying the calculus of limits to the hypotenuse in the Pythagorean theorem. So that's pretty easy to remember. Find the length of this parametric curve on the interval where t goes from 0 to 10. now we can do this. And we've got our formula. The length is the integral of square root dx dt squared plus dy dt squared dt, where dx dt is going to be the derivative of t cosine t minus sine of t. What's that derivative?
For the x, you said?
Yeah, what's dx dt?
Cosine of t minus t times sine of t. Wait a minute. Yes, I think.
So x is t cosine t minus sine t. Don't forget about the minus sine t part. Because when we take the derivative here, you're right to use the product rule, and I think you used the product rule correctly. You got cosine t plus t, oh sorry, you're right, it was minus. Because the derivative of cosine is negative sine, so minus t sine t. But then don't forget about the last minus sine t, because the derivative of sine is cosine. So actually, dx dt is just negative t sine t. Okay, dy dt is also a case where I have the derivative product rule for t sine of t. That's going to be sine of t plus t cosine t. And then I have to take the derivative of cosine d, which is going to be negative sine of t. So here, the derivative will be t cosine t. And now I have to square these, add them up, take the square root, take the integral, everything you see in the formula here. And dx dt squared will be t squared sine squared t. dy dt squared is going to be t squared cosine squared t. So it simplifies like this. How do I simplify the radicand?
Well, sine squared plus cosine squared is 1.
Sine squared plus cosine squared is 1. And that means this simplifies to
2t squared plus 1.
Would it just be t squared?
it's just t squared. Because you got to think about factoring out the t squared first, and then you get sine squared plus cosine squared, and then you make it a 1, and then you're just left with that t squared you factored out. Well, that's nice. What's the square root of t squared? t. And, our lower bound was always 0, and our upper bound was always 10. So I'll go ahead and throw in my lower bound and upper bound here. Now when I take the antiderivative of t, I get what?
1/2 t squared.
1/2 t squared. And I've got to plug in 10 and 0 here. And 10 squared is 100. Half of 100 is 50. Nice. So the length of that parametric curve on the interval where t goes from 0 to 10 is 50. And this always makes me curious to know, like, what is this parametric curve? What does it look like? We open up Desmos and we say, I want t cosine t minus sine t. And t sine t plus cosine t. And we're going to allow t to go from 0 to 10. That's what it looks like. And we're saying the length of this curve is 50. That kind of seems about right. I had to guess. Doesn't sound outrageous anyways. Okay, any questions about this one? Okay, so that's how you find the length of a parametric curve. This is how we find the length of an explicitly defined curve. In other words, what if I have y given to me as a function of x? The quickest and easiest explanation here is that I could start by writing down the formula we derived for a parametric curve. And that was true for every parametric curve. Now, what if I were to factor out that dt, right? If I factored in the dt, it would be like dt over dt. This is the same thing as because these dt squareds in the denominator inside the square root cancel out this dt in the numerator on the outside of the square root. And then what you would want is to multiply everything by dx over dx, which is like multiplying by 1, right? Multiplying by 1 never changes the value of anything. But what we'll do is we'll distribute the denominator inside the square root, and distributing the denominator dx inside the square root makes it squared. I'm left with that dx in the numerator. And then now you say, well, dx over dx, that's just the number 1. And so in the end, we get dy dx squared plus 1 dx. Really, the trickiest part about this explanation is just the algebra. If you've got something like the square root of 3 squared plus 4 squared, and you wanted to multiply by like, I don't know, 5/5. This is the same thing as 3/5 squared plus 4/5 squared times 5. And I'm skipping like some intermediate step, maybe, I guess, but whenever I move something inside of a square root, you have to square it. And then you split the fraction there where the plus sign is. If you've got 3 squared over 5 squared, that's the same thing as 3/5 squared. And so maybe that's, if you're confused about what's happening there, that's kind of the trick. Questions? No. So if you have an explicitly defined curve, now you know what formula to use. We say that the length of the curve is going to be the integral of the square root of dy dx squared plus 1 dx. So this time I have a curve y equals x cubed over 6 plus 1/2x. What is dy dx?
One-sixth 2x squared plus 1/2. Okay, so minus 1/2 x to the negative 2.
Yeah, I think you are just about right, because this is 1/6 x cubed plus 1/2 x to the negative 1. And so with the power rule, we bring down the power, and that becomes 3/6, which is 1/2 x squared minus 1/2 x to the negative 2 power. Okay, now with the length formula, we've got the integral from 0 to 1 of the square root of this squared, right? I don't just need dy dx, but I actually need dy dx squared. So let's square this. And you have to think about foiling, right? First outer, inner, last. The first term is going to be 1/4 x to the 4th. Outer and inner are the same thing, so I'm going to multiply by 2. And so 1/2 times 1/2 times 2 is just going to be 1/2. And then there's going to be a negative. X squared times x to the negative 2 power is it's just 1, right? X squared divided by x squared. The last term is going to be negative times negative, which makes it a positive, a half times a half, which makes it a fourth. And then x to the negative 2 times x to the negative 2 is what?
X to the negative 4.
There you go. X to the negative 4. Okay. What happens when I add 1? Because here in the radicand, I'm going to have dy dx squared plus 1. Well, if I were to add 1, that's going to make it 1/4 x to the 4th plus 1/2, right? Because I'm adding 1 to both sides. And what do I know about this problem? I know that I'm supposed to take a square root of this expression. It would be really nice if this polynomial, well, I guess it's not a polynomial because I've got x to the negative 4, but it would be really nice if this expression were a perfect square. I don't have any guarantee that it's a perfect square, but I am trying to take the square root, right? So is there any way that this is a perfect square? In other words, what two things could I multiply together to get this trinomial, right? Or it's supposed to be just be one thing squared that gives me this. And the only hope I have is like if I have x squared plus x to the negative 2 power, because I've got to get x to the fourth and x to the negative 4. What kind of coefficients should I use? I guess I have to use 1/2, right? Because 1/2 times 1/2 gives me 1/4, and 1/2 times 1/2 gives me 1/4. Does that work though? Because the first term squared gives me 1/4 x to the fourth. The last term squared gives me 1/2 x to the negative 4. What if I multiply 1/2 x squared times 1/2 x to the negative 2? That would give me 1/4, right? But then I get two of those terms because I get first, outer, inner, last. And outer and inner are the same thing when I square it. So that means 1/4 plus 1/4 gives me 1/2. That actually works, right? That's a way to factor that expression. And again, the only reason I was even looking for a way to take the square root is because I've got this big square root in my integrand. And so I'm trying to take the square root of 1/2 x squared plus 1/2 x to the negative 2 power. And ordinarily, if I was looking at this thing, I wouldn't even think to try to factor it, right? That looks like just a big, ugly algebra expression. The only reason I thought about trying to factor that as a perfect square is because I do have a square root. So now, the square root cancels with the square. And now I'm taking the integral from 0 to 1 of 1/2 x squared plus x to the negative 2. And so the antiderivative of x squared is 1/3 x to the 3 power. And the antiderivative of x to the negative 2 power would be -1 times x to the negative 1 power. So I got 1/2 times 1/3 is 1/6. Oh. I see an issue. Right? I can't divide by 0. Nobody's allowed to divide by 0 in this class. So this problem's not very well written. Really, I should have seen the issue from the start. And if I have this issue on the homework, I'll make sure I go back and fix it. But it's x cubed over 6 plus 1 over 2x. Do you see how if I was going to take the integral, or sorry, the length of this curve from 0 to 1, this curve is infinitely long. It just keeps going up forever and ever and ever. So this curve length is infinity. What I should have done is instead of 0 to 1, maybe say 1 to 2. That would have been a better thing to do. But that's okay. We'll fix that for next year. We'll say the lower bound is 1, the upper bound is 2, and fix it everywhere until we get down here and make that lower bound 1, upper bound 2. And in this case, 2 cubed is 8, and so I'm talking about 8/6 minus 1/6 plus negative half times half. Two negatives make a negative, and this is going to be half of half is a fourth, and then 1 times half is half. So 8/6 minus 1/6, 7/6 minus a fourth minus a half is negative fourth. Two negatives make a positive. And the common denominator is going to be 12. So I will have 14/12 plus 3/12, which is 17/12 as my length. Cool. So yeah, if I give you the right balance, this problem's not terrible. But the hardest part is that little algebra trick, I think. And you just have to say, well, I'm trying to take the square root of it. Is it possible to take the square root? It's not always possible, but sometimes you can. It should be possible to take the square root for any problem I give you on your homework or test review. Whenever I pick test problems, I just copy and paste them from the test review. So, questions? No? All right, the last thing we're going to talk about today is a surface area of revolution. And if you want to find a surface area of revolution, here's the formula. The explanation for why this formula might work is, well, if we have an xy plane, and here's my curve, and we already know that part of the stuff you see in the integrand is from the Pythagorean theorem, right? That should look really familiar to you as like being part of the curve length formula. Because what I've underlined here in orange is like a little line segment along this curve. The length of this little line segment. What the y is telling us, the y is the distance, instead of obviously the y coordinate, so it's the distance from the axis of rotation, which we've decided is going to be the x-axis, up to where that little line segment happens. So y is this vertical distance. That's why it appears in the numerator. And then the 2 pi is because 2 pi y is the circumference of a circle with radius y. Sorry, that's supposed to be a circle, not a 0. So if I write 2 pi y times the length of this orange line segment, it's the circumference of a circle times the length of the line segment. It's kind of going to give me the lateral surface area of a very short cylinder. And the width of this cylinder is the length of this line segment. And technically, if this is a straight line segment in orange, it could be at an angle, right? It doesn't have to be horizontal flat. And that means this is not technically a cylinder, but it's like a slice out of a cone. It's got a little bit of an angle to it. But the good news is that if you use the y-coordinate that's halfway in between the y-coordinates at the ends of this line segment, then you do get the lateral surface area of a slice of a cone. Turns out it balances. And then as we take the limit and the number of these slices goes to infinity, you get exactly the surface area of revolution we're talking about here. What's the surface area if you rotate this blue curve around the x-axis? That's the formula. So that's going to be another one to memorize. I know, I'm sorry you have to memorize so many things in this class, but that's another geometry formula in addition to the disk method and the washer method and the shell method and the curve length formulas. Now you got a surface area formula you got to memorize. But find the area of the surface formed by revolving the curve y equals x cubed on the interval 0 to 1 about the x-axis. So I'll draw a little picture first.
I have a question with the formula.
Uh-huh.
It's y times the square root, right? Not like y on the root.
It's y times the square root, yeah. So here's the y equals x cubed curve. And we're talking about what would happen if I rotate this around the x-axis. It's going to make a surface. I'm going to plot it just because I need to practice my GeoGebra skills. Because the way, if I don't use GeoGebra, I'm going to forget how to use it. It's I already forgot. I have to type in curve, t comma t cube comma t comma 0 comma 1. That's how you plot y equals x cubed, by the way. It's not ultra user friendly. And then you want surface of revolution. Grab that sucker and boop. Okay, that's the surface. We're wondering what is the area of this surface. Looks like a French horn to me, if you're a band nerd. Okay, now let's just bring out the formula that we just discussed. The surface area. Ooh, did I have another typo? I think I had a typo from like copying and pasting. Yeah. I probably shouldn't use capital L for surface area. I should probably use like SA for surface area. So it's two things to fix in my lecture notes. But this is the surface area. It's going to be 2 times pi times y, where y goes inside the integral but outside the square root. And the square root's going to be dy dx squared plus 1 dx from 0 to 1. So this integral is with respect to x. So I can't have a y hanging out. What am I going to put inside my integrand instead of y?
A cube root of x.
You're overthinking it. Because y is equal to x cubed, so I'm just going to write x cubed. Okay, next I need, what is dy dx?
X squared.
3x squared. And so dy dx squared would be 3x squared squared also known as 9x to the fourth. How do I solve this integral?
You might be able to use trig sub.
You could use trig sub. That would work, but it would also be the more difficult way of solving things. There's an easier way.
Probably use U substitution.
U substitution. What should U be?
X to the 4.
Let's just make it the whole thing 9x to the fourth plus 1. So then the derivative would be 36x cubed I see an x cubed dx. Of course, I'll have to divide by 36. And 2 divided by 36 is 1 over 18 times pi times an integral from 0 to 1. Oh, hold on. Getting ahead of myself. Times an integral of square root u du. I like to write u to the 1/2 du because it's going to help me with the antiderivative in a second. By the way, do you know how I should treat these lower bounds and upper bounds of my integral? Do you know how to do this?
You have to plug them into the U.
I have to plug them into this u formula, so my lower bound is not going to be 0 anymore. It's going to be
1.
Yes. 9 times 0 to the fourth plus 1 is 1. My upper bound is not 1 anymore. It's going to be 10. 9 times 1 to the fourth plus 1 is 10. Now we take the antiderivative of u to the half, which is going to be u to the 3/2 times 2/3. So we'll have pi over 27 times 10 to the power 3/2 minus 1. And now I want to know, what is pi divided by 27 times 10 to the 3/2 minus 1? $3.563 ish. If I just had a circle with radius 1, the area would be pi. And this should have an area a little bit larger than a circle with radius 1, because there, that flat shape is a circle with radius 1. And it's getting more area when we pinch the middle of the circle and bring it up a little bit. That only increases the area. So I'm looking for an area that's just a little bit more than pi. I'm looking for an area that's just a little bit more than 3.14. And that seems right. That sounds like we're in the right ballpark for a solution. And if if you don't make any obvious mistakes and your solution seems like it's correct, then you're good. You just don't want to have a negative answer or like super giant answer, super tiny answer. Here we go. Find the area of the surface formed by revolving the curve about the y-axis on the interval. So let's draw a picture. Oh, by the way, did you guys have any questions about this last example? Did that make sense? Okay. Let me draw a picture of what we're doing now. Oh, the interval is from 0 to 4. There we go. Much better. And so we're taking this curve and we're revolving around the y-axis. So I don't really like this because my formula that I memorized is about revolving around the x-axis instead of the y-axis. But I could maybe notice that this would be the same area as, what if I just switch the symbols? Then I could say switch the y to an x and the x to a y. And then switch rotating about the y-axis to rotating about the x-axis on the interval from 0 to 4. And I get the same shape, right? It's oriented differently, but I get the same exact shape. And again, this is because it doesn't really matter whether we use an x or a y or y and x. You just got to be consistent with how you're doing it. So in my problem in orange, I changed all of the x's to y's and all the y's to x's. So now we're rotating about the x-axis. Now x goes from 0 to 4. And now x is equal to y squared. And of course, if x is equal to y squared, that means y is equal to square root x. I like this problem better because I have already memorized the formula for how to find the surface area. And the surface area is 2 times pi times y, where y is inside the integral. And I multiply that by a square root of dy dx squared plus 1 integrate with respect to x. X goes from 0 to 4. By the way, y is equal to square root of x. And so I'm going to use that here to replace that y with square root x. And then also, what is dy dx?
2x. Oh, wait.
So you're looking at the blue problem, but we've translated this into the orange problem now. And so for this y, what is the dy dx?
1/2 x.
1/2
Y.
x raised to the power
-1/2.
-1/2. Yeah, because in the derivative power rule, you subtract 1 from the power. So instead of having x to the half power, we have 1/2 x to the -1/2 power, taking a derivative. And what then would I get if I had dy dx squared? Because I'm going to need that for my radicand there. Well, half squared is 1/4. What's x to the -1/2 squared? Just x to the -1. Because, I'll explain. If I have x to a -1/2 power and then I square it, I can just multiply these two powers. And so it's like x raised to the power -1/2 times 2. And half times 2 is 1.
Yeah, I squared the half. That's my bad.
That's all right. So then we get surface area equals 2 times pi times integral of y is square root of x. Or another way to write that is y equals x, we'll just say square root of x, times the square root of 1/4 x to the -1 power plus 1 dx. Okay, so what we can do is multiply the radicands. Did you know that if you have two square roots side by side, you can just multiply those? Right? So that means here in our problem, where I've got 2 pi integral of these two square roots, I can just multiply those two square roots together. And x times x to the -1 power, those cancel each other out. And x times 1 is x. It's pretty good. How do I solve this antiderivative? Do you know what strategy we should use?
Do we just split it up? Oh, no, we can't.
You can't split up a radical like that.
Could you do the u squared? Wait, no, never mind. That's not right either. Would it just be a u substitution?
I should say u equals
1/4 plus x.
1/4 plus x. And that way du is equal to dx. So we write 2 pi integral square root of u is u to the half, dx is du, what are my new lower bound and upper bound?
One-fourth of 5/5.
1 over 4, and 4 plus 1/4 is like 16/4 plus 1/4, which is 17/4. So now I've got 2 times pi times the antiderivative of u to the half. That's going to be u to the 3/2, and you multiply by 2/3 for that antiderivative. And then upper bound 17 over 4, lower bound 1 over 4. So we get 4 pi over 3 times 17 over 4 to the power 3/2 minus 1/4 to the power 3/2. 1/4 to the power 3/2 is actually just 1/8. That's doable, but the 17/4, I don't know. Don't know about that one. I don't think it's possible because 17's prime, isn't it? So then I'll go ahead and just type in my calculator. 4 times pi divided by 3 times, open parentheses, 17 raised to the power 1.5 divided by 8 minus 1 over 8, close parentheses. And I'm thinking it's 36.18. Now the question is, does that sound reasonable? 36.18.
How would you check your work if you wanted like an exact?
If you wanted to check your work exactly?
Yeah.
You know, it's, yeah, I was about to say it's prone to make mistakes, but we could go to AI and ask it the question and see what it would say. You could try copying and pasting into AI and see if it gets the right answer. If you want an approximation just to like check, does this sound about right? I might think about a cylinder in this case, like what's the lateral surface area of a cylinder that has a height of 4 and a radius of 2? Well, the circumference of that cylinder would be 2 times pi times 2, which would be 4 pi, and then a height of 4. So it'd be like pi times 16. So a lateral surface area of a cylinder with radius 2 is pi times 16, which is 50. And I would expect that this surface area should be less than 50 because it pinches down here. And so this part isn't the full radius of the cylinder that I'm comparing it against. So it sounds right. I mean, that sounds reasonable. But yeah, if you wanted to actually check your work, you'd have to probably use AI. I mean, you could also just plug in this integral into something like Wolfram Alpha. But then the question becomes, well, did I set up this integral correctly? In which case, AI is probably your better bet. Okay, recall that the hyperbolic cosine function is the even part of e to the x, and hyperbolic sine is the odd part of e to the x. Starting from these definitions, prove that cosine hyperbolic minus sine hyperbolic is equal to 1. Oh, sorry, I forgot to say squared. Cosine hyperbolic squared minus sine hyperbolic squared is equal to 1. Let's try to prove that. So if you remember, the even part of a function is the function plus the function evaluated with a negative argument divided by 2. And the odd part of a function is the function minus the function evaluated at a negative argument divided by 2. So if I wanted the even part of e to the x, x, this would be e to the x plus e to the negative x divided by 2. And if I wanted the odd part of e to the x, this would be e to the x minus e to the negative x divided by 2. So that's what I mean by these definitions. Now what we're trying to prove is that this is true. This is what we'd like to verify. And that means if we're trying to verify this, we just got to plug in these old definitions, like e to the x plus e to the negative x divided by 2 squared minus e to the x minus e to the negative x divided by 2 squared is equal to what? I don't know. Well, dividing by 2 and then squaring that is the same as dividing by 4. So let's put a big 1/4 in front of everything. Then I have to FOIL this stuff, right? First, outer, inner, last. And that means I get e to the 2x plus, what is e to the x times e to the negative x? What's e to the x times e to the negative x? 1. So I'm going to get 2 of those terms, and then e to the negative x times e to the negative x is a term that looks like e to the negative 2x minus e to the 2x, and then first, outer, inner, last, I get the middle terms, which are e to the negative x times negative e to the negative x. That's going to be a -1, but I get 2 of those terms. And then the last term is going to be negative e to the negative x squared. So the square takes away the negative, but I forgot to distribute this minus sign to the 2. Sorry about that. I'm distributing that minus sign. And then I'm thinking about the last term again. E to the negative x squared is e to the negative 2x. Plus I have a minus. So I've got minus e to the negative 2x. All right, so just to color code this for you. The first term gives me this trinomial when I FOIL it. The second term here gives me this trinomial when I FOIL it. You gotta be careful distributing that minus sign. And now when you look at it, you think, oh yeah, some of that stuff cancels. And this would simplify to 1/4 times 2 plus 2, which is 1. So cosine hyperbolic squared minus sine hyperbolic squared is equal to 1. Okay, the next part of this question says, then this fact will help you find the length of the curve given by y equals cosine hyperbolic of x on the interval from -1 to +1. What does the curve y equals cosine hyperbolic look like? I don't know if you guys remember from earlier this year, but we talked about this. It's called the catenary. Catenary is the shape of a hanging chain. It's not a parabola, but this is actually then the length of a chain hanging between two equal height posts. You know, and if you know the distance between the posts is like -1 to 1 or 2, how long is the chain? If it's about this droopy. So let's do it. Let's use our curve length formula. And the curve length formula, I believe, would be for an explicitly defined function. The square root of dy dx squared plus 1 dx. And y is cosine hyperbolic. Do you remember what is the derivative of cosine hyperbolic?
Sine hyperbolic.
Yep, it's just sine hyperbolic. Not a negative, just a positive sine hyperbolic. It just flips back and forth between sine and cosine. It's not like on a 4 cycle like the originals. It's on a 2 cycle. So that means the derivative squared is going to be sine hyperbolic squared. What is sine hyperbolic squared plus 1? Nice. Yeah, we used that identity we just proved a moment ago, this one right here, to say that sine hyperbolic squared plus 1 is the same thing as cosine hyperbolic squared. Well, the square root would cancel the square, and now we're talking about the integral of cosine hyperbolic. The integral of cosine hyperbolic would be sine hyperbolic, yeah, because these derivatives just flip back and forth. So the antiderivative of cosine is sine hyperbolic, and this entire time the lower bound was actually -1 and the upper bound was +1. So I'm talking about evaluating sine hyperbolic at 1 and at -1, subtracting, and you get the difference here. So depending on how advanced your calculator is, you could do this. It's also that sine hyperbolic is an odd function, right? It's the odd part of e to the x. And so plugging in the -1 is the same thing as flipping the sign and making it positive. So this is actually the same thing as 2 times sine hyperbolic of 1. And sine hyperbolic, by the way, has the definition e to the x minus e to the -x divided by 2. So the 2's cancel, and you get e to the 1 minus e to the -1, which is e minus 1 over e. So whatever that is. E minus 1 over e is 2.350. Close to that. And again, that seems about right, because if my 2 posts are a distance of 2 apart, I expect this chain is going to be a little bit longer than 2. I don't know how much longer, but 2.35 seems like it's a little bit longer than 2.
Does this
Sounds reasonable.
have the hyperbolic?
No, not that I can tell. I don't think it does. But it's got e to the x on it. So, yeah, questions? So in this way, the sine hyperbolic function kind of gives you a formula for the length of the catenary. The cosine hyperbolic is the shape of a hanging chain, the shape of a catenary. But if you want to know what's the length of a hanging chain, you have to use the sine hyperbolic function to tell you the length. So that's the only useful application I know of the hyperbolic trig functions. I've got one more for you that maybe we can solve in the next 3 minutes. Find the length of the curve y equals x squared on the interval from -1 to +1. What an easy looking question, right? Like you've been seeing y equals x squared since 8th grade, and now you're thinking, that looks so easy. What a simple little function. We've got my y-axis, my x-axis, the interval from -1 to 1, of course, the curve is a parabola. So it's going to dip down and come back. Here's 1. Super easy. How hard could it be to find the length of this curve? Well, dy dx is 2x. So if I wanted to square this, that would be 4x squared. And if I want to apply my length formula, this is going to be the square root of dy dx squared plus 1. So in other words, 4x squared plus 1 dx. Okay, so I'm going to need to use trig substitution, because I've got something squared, like a variable squared plus a constant squared. Where I see like u squared plus a squared, so I'm going to set u equal to a tangent theta, and that means 2x is equal to 1 tangent theta. And then I draw myself a triangle for the trig sub, and here's theta. Tangent is the ratio of opposite to adjacent, and that makes my hypotenuse 4x squared plus 1. So I'm thinking about the trig function that would give me my integrand, square root of 4x squared plus 1, and that would be the ratio of hypotenuse over adjacent, which is secant. And now I have to convert dx into a d theta. If x is x is 1/2 tangent theta. Dx is 1/2 secant squared theta, d theta. So that means my length is going to be something like this. So my length is going to be 1/2 times the integral from -1 to 1 of secant cubed theta d theta. Piece of cake, right? So you remember the integral of secant cube? Maybe you remember it, maybe you don't. But remember, you have to use integration by parts, split one of the secants apart from the secant cube, so that you take the derivative of secant and the antiderivative of secant squared, and then you do the integration by parts formula one time, and then you notice that the antiderivative of secant cube comes back again in the integration by parts formula. So you rearrange that equation, you divide it by 2, and then you still have to take an antiderivative of secant, and then you do that one way or another. Maybe you remember it. It's natural log of secant plus tangent. And then, yeah, it's the whole thing. Whole thing. And then you've gotten the antiderivative in terms of thetas, right? And so then you have to reverse that by saying that, well, theta is the arctangent of 2x, right? And then you got to mess around with your triangle again to get it in algebraic form. And then one day you would eventually find the length of this curve. It would take a long time, but it's possible. Okay. You guys have a good day.